A substance which prevents clotting is introduced into the animal's blood. The dog is under an anesthetic. It doesn't feel pain. No interruption of the animal's normal functions has yet occurred.
For 175 years, doctors have been switching off human consciousness on purpose, millions of times a day, without ever fully knowing how the drugs actually do it. This summer, a piece of that mystery finally cracked open. It's one of the strangest facts in medicine. Anesthesia is among the safest, most routine things we do, and also one of the least understood. We've always known that it works. The question that's lingered since the very first surgery under ether is exactly how a drug reaches into the brain and takes consciousness offline so precisely that you can hand your entire body to a stranger and feel nothing at all. Start with the basics. Your brain is an electrical organ. Neurons talk to each other in tiny pulses of current, and everything you are, every thought, every sensation, the fact that you're awake to read this, rides on that constant crosstalk. Anesthesia works by quieting it. Turn the conversation between neurons down far enough, and awareness fades. Different anesthetics do that through different doors. The drugs we push through an IV, like propofol, mostly lean on the brain's own calming signal and amplify it. But a lot of surgery runs on a different kind of anesthetic, the ones you breathe, the vapors, like sevoflurane. And for decades, we've suspected those gases work partly by tampering with something called ion channels, the microscopic gates that let a neuron fire. Suspected. What nobody had ever done was actually catch one of these drugs in the act. That's what changed. Researchers at Weill Cornell Medicine and Birkbeck, University of London, captured the first atom-by-atom snapshot of an inhaled anesthetic grabbing onto a sodium channel. And to picture why that matters, picture the channel itself. It's a gate in the wall of a neuron. When it flicks open, sodium rushes in, and that inrush is the spark that fires the cell. Open enough gates, and the message travels. What they found is that sevoflurane doesn't plug the gate head-on. It slips into a small pocket off to the side of the channel and holds it in its closed, resting shape, so the gate is slower to open and the neuron is slower to fire. Do that across billions of neurons at once, and the whole electrical conversation drops to a murmur. That murmur is what unconsciousness looks like at the level of a single protein. The way they proved it is honestly my favorite part. Our own sodium channels are enormous and tangled, too complex to image cleanly. So the team borrowed a stand-in from a marine bacterium, a tiny organism that uses a much simpler version of the same channel to swim toward food and oxygen. Simple enough to crystallize, simple enough to X-ray. And then, to make sure they'd found the real spot, they changed a single building block inside that pocket, one amino acid, and the drug lost its grip. It couldn't hold the gate shut anymore. Change one atom's neighborhood, and the anesthetic stops working. That's about as close to a smoking gun as this kind of science gets. Now, the honest boundaries, because this matters. This is one target, not the whole story. Anesthesia acts on several systems at once, and no single channel explains all of it. The bacterial channel is a stand-in that still has to be matched back to human biology. And finding the switch is not the same as explaining consciousness itself. What this is a real, physical foothold on a question that's been almost entirely theoretical for a century and a half, and it opens doors. If we know the precise pocket these drugs bind, we can start designing anesthetics that hit it more cleanly with fewer side effects. It might explain why some people react to anesthesia differently than others, and further out, it gives neuroscience a new handle on the oldest question of all: what consciousness actually is, and how it can be lifted and set back down. Here's what stays with me. For most of medical history, we trusted anesthesia the way you trust a bridge you've crossed 1,000 times, not because you understand the engineering, but because it's always held. Every day all over the world, people have handed over their consciousness on that trust, and it has held. What this discovery represents is the slow, patient work of turning that trust into understanding. One atom, one pocket, one channel at a time. We were never reckless with the mystery. We were just honest that it was one. And now, 175 years in, we know a little more about the thing we do every single day. See you in the next case.